Okay, welcome to Let's Get to the Marks. We're looking at A-level chemistry. We're going to do a weak acids question. So this is from the 2023 paper one for AQA A-level chemistry. Question 10. This question's about weak acids. 10.1. Table 5 shows the pH ranges of some indicators. Hopefully you remember what an indicator is. It's a chemical that changes color when it changes pH. So bromocresol green has a pH range of 3.8 to 5.4. That means it changes color within that pH. Bromothymol blue 6 to 7.6 and thymol blue 8 to 9.6. Identify the indicator that would be most suitable for a titration between propanoic acid and sodium hydroxide. Pause the video, have a go. Now hopefully you will remember that propanoic acid, an organic acid, a carboxylic acid, that means it's a weak acid, partially dissociates in solution. And sodium hydroxide is not a string, it's a strong base. Okay. And so we want to find the endpoint, or the equivalence point needs to be between a weak acid and strong base, not we don't want our pH range for our indicator to be either in the pH of a weak acid or a strong base. So a weak acid is what, 3, maybe 4 to 6. So we don't want an indicator that changes color between 4 and 6 because it will change color if I have the weak acid in the conical flask. We don't want an indicator that changes color between like 12 or 13 to 14 because that will change color if I have my strong base in the conical flask before we've even done the titration. So which ones are out of the question here? We can't do 3.8 to 5.4. So bromocresol, no good with weak acids. Bromothymol blue, not really good with weak acids because it can change color at pH 6. So if your weak acid is there, it's going to change color already. So the only usable one is thymol blue, which will not change color if you have the weak acid or the strong base in the conical flask added with the indicator. Okay, cool. So thymol blue is your answer there. Right, let's go down to 10.2. Give the expression for the acid dissociation constant Ka for propanoic acid CH3, CH2, COOH. Now, we want the dissociation constant. We want the expression for it. So you should remember with Kc or Ka, you're looking at products over reactants, the concentration of the products over the concentration of the reactants. What we have to think about when we're dealing with the dissociation of a weak acid like propanoic acid is, what are the products? Well, propanoic acid would be the reactant, so that's CH3, CH2, COOH. What would it break down into? You should remember that propanoic acid will break down into propanoate ions, which is CH3, CH2, COO with a minus sign because it's a negative ion. And those hydrogen ions will come off. That's why it's an acid. It releases hydrogen ions when it dissociates. And so those will be the reactants. So we want to put the reactants over the products. And here's the equation for that. We use a reversible symbol because it's a weak acid. Strong acids, we wouldn't use this reversible symbol. And it forms the propanoate ions or carboxylate ions and hydrogen ions. Now, one thing I've got to add to my expression is I need to show that I'm dealing with concentration and I'm not dealing with moles or something else. And the way to show that, do you know how to show concentration in an expression like the Ka expression? You should add, and you probably know this, you've got to add square brackets. Now, you must make sure they're squared off. And I know you might think, does it really matter? It does matter. If you use curved brackets are used for pressure. Square brackets like this are used for concentration. So we have the concentration of our reactants here over the products. Apologies if you can hear the sound of my daughter running around and screaming in the background and shouting, asking me for another frube. Can I have a strawberry frube? Blah, blah, blah. There we go. Right, so yeah, little note, make sure you use square brackets for concentration, rounded brackets for pressure. Okay, we're going to move on to 10.3. Calculate the pH of a 0.1 mole per decimeter propanoic acid solution. Give your answer to 2 decimal places for propanoic acid where the pKa is 4.87. Okay, so just highlight here, this is the expression we're using. We want to find H+. If you want pH, you've got to do the minus log H+, or the hydrogen ion concentration. That's what the pH is. So what we're really doing here, we want to rearrange this equation that we had in 10.2 to make hydrogen ions the subject of the equation. So how are you going to do that? Well, we can start by saying hydrogen ion squared. At the top, we can rewrite the expression with hydrogen ion squared because we know that the concentration of the H plus is equal to the concentration of the carboxylate ion, so we can just make that H plus squared. So then we can rearrange this by doing Ka times the concentration of the acid square rooted, and that will give us the hydrogen ion concentration. Now, we need to find Ka because they've given us pKa, which is really cool. Like if you want to plot Ka on a graph, it's really unwieldy because it's often times 10 to the minus 7 or something like that. So pKa gives you nice numbers for plotting in graphs. So we often convert Ka, the acid dissociation constant, to pKa. Well, we need to convert pKa back to Ka to put in this expression. And what you do there is you go shift minus log pKa, and that gives you the Ka. So press shift on your calculator, minus log, and then put in 4.87, and you're going to get 1.3489 or 1.35 times 10 to the minus 5. Now that's the Ka, so we want to times that by 0.1, which is the concentration of our acid circled here. And then we want to square root the answer. And if we do that, we get 1.16 times 10 to the minus 3 mole per decimeter. And that's our hydrogen ion concentration. But we're not done yet. This will have secured us 3 marks. So rearranging the expression and then finding the Ka from the pKa will get you 2 marks. Now we've got the hydrogen ion concentration. Hopefully you can remember how to work out the pH from the hydrogen ion concentration. And pH is the minus log of the hydrogen ion concentration. So get your calculator out, press minus, then press the log button, and then put in 1.16 times 10 to the minus 3, press the equal sign, and you're going to get the pH. Now, for the 4th mark, so this will get us our 3rd mark, working out the pH here, he says, although, yeah, zing this in my calculator, guys. And we get the number 2.93616, and that's the pH of this propanoic acid solution. However, don't forget that this question asks for us to do this to 2dp. That means 2 decimal places. And always forget these things. That's why you must use a highlighter or circle or underline the stem of the question. So we're going to round that up to 2.94 because the 6 is bigger than the 3. So instead of 2.936, it goes to 2.94, 2dp. Awesome. That's the end of the question. Let's get on to the next part, 10.4. Okay, so for 10.4, here we go. This is more of a kind of buffers, similar to a buffers question, because you're dealing with a weak acid and the salt of the acid. So for butanoic acid, the Ka is 1.15 times 10 to the minus 5 mole per decimeter. We've got 20 centimeters of 0.1 mole per decimeter sodium hydroxide solution. That's added to 25 centimeters of 0.1 mole per decimeter butanoic acid solution. Calculate the pH of the solution form. First of all, we need to look at the reaction. Sodium hydroxide with a carboxylic acid with one hydrogen ion to give away is going to be a 1-to-1 reaction. So now we're going to work out the moles of sodium hydroxide and the moles of butanoic acid. And you can do that with the N over CV. And this is going to get you 2 out of 5 marks, even if you can't do the rest of the question. So just stick to the basics. You've seen volume, you've seen concentration, so N over CV. So we're going to do 0.02. Remember, you have to divide centimeter cubed by 1,000 in these questions. So we've got 0.02 times 0.1, and that gives us 2 times 10 to the minus 3 moles of sodium hydroxide. Now for butanoic acid, we've got 0.025 for the volume, decimeters, times 0.1 is going to give us 2.5 times 10 to the minus 3, and that is the moles of the carboxylic acid. Now, when the acid and alkali neutralize together, we're going to have an excess of one of them because they're not quite 1-to-1. It's a 1-to-1 ratio, but the amounts we have are not 1-to-1. So we're going to take the bigger amount, which is the acid, 2.5 times 10 to the minus 3. We're going to subtract 2 times 10 to the minus 3 for the sodium hydroxide. We're going to be left with 5 times 10 to the minus 4 moles of acid left over. Why is this important? This would have secured you 3 out of 5 marks, which is pretty cool, right? So you've worked out the excess acid. And this is because we're going to use the buffer equation. And for the buffer equation, when you're working out the pH of a buffer, you're going to do the hydrogen ion concentration is equal to the Ka times the acid over the salt. Now note, when you've got a strong alkali or base like sodium hydroxide, it's going to fully dissociate just like a strong acid. So that is going to fully, and in this equation, actually, the sodium hydroxide is fully reactive because we had excess acid. It's all been used up. So we know exactly how much salt we've got of, we know that we've got, what was it? Propanoic acid, butanoic acid. So we know we've got like 0.2 moles, 2 times 10 to the minus 3 moles of sodium butanoate, which is the salt. So we're going to do the amount of acid left over, which is 5 times 10 to the minus 4, divided by the concentration of the salt, which is equal to the concentration of the base. Okay, so, and then we're going to times that by the Ka. So 1.15 times 10 to the minus 5 times the acid, which is our excess left over, multiplied by the salt. Remember, there's no base left here. You're not doing acid divided by base. You're doing acid over salt. Just so happens that the salt is equal in moles to the base. Now, we could, if we want, turn this into concentration by dividing by the volume, and we're told that we've got 20 and 45 centimeters, so we've got 0.045 decimeters, so I could divide all these moles by that, but they're going to cancel out, and it's a ratio, so I can just use the molar ratio, and we're going to work that out as 3.775 times 10 to the minus 6. That's the hydrogen ion concentration, and you'll get the exact same answer even if you convert the moles of the acid and moles of the salt into volumes. You'll get the into concentrations, you'll get the exact same. And when we minus log that in our calculator, press minus, press the log button, the bracket will come up, put in the 3.775 times 10 to the minus 6, and you'll get 5.42 as the pH. And that is the answer for 5 beautiful marks. All right, guys, we're moving on to the very last part of the question. So let's zing. Here we go. 10.5. A student plans to titrate butanoic acid solution with a solution of ethylamine. Explain why this titration cannot be done using an indicator. So pause the video, have a go. Okay, you should spot butanoic acid, carboxylic acid. It's a weak acid, partially dissociates. Ethylamine, weak base. What's the issue? Well, our weak acid's going to be like pH 3 to pH 6. Our weak base is going to be pH like 8 to 11 or 12. And this means we're not really going to get a really straight vertical section at the end point when we carry out the neutralization. We're going to get a gradual change because of this, and therefore there'll be no suitable indicator for that. So the 2 marks, one for saying spotting that you're dealing with a weak acid and a weak base, and the next one for spotting that you won't get a straight line at the end point, you're going to get a gradual curve. And there we go.
You're still
Let's get to
here?
the marks.
It's over.